So have you ever found yourself staring at a log, wondering why your pods are getting killed or why your app is suddenly grinding to a halt for no obvious reason? Well, if that sounds familiar, you are in exactly the right place. Today, we're diving deep into one of the most critical and honestly most misunderstood topics in Kubernetes: resource management.
Here's how we're going to break it all down. We're going to start with the problem itself. Then we'll explain the core concepts of requests and limits. After that, we'll see how Kubernetes decides which pods get to live, what happens when things go wrong, and finally, we'll wrap up with some solid best practices you can start using right away. All right, let's get into it.
All right, let's kick things off with a situation that I bet a lot of you have been in. You deploy your app, everything's looking good, the lights are green, and then, out of nowhere, things start to go sideways.
Yeah, if those questions sound familiar, then you've definitely run into resource contention. OOMKilled just means out of memory killed. It's Kubernetes' way of saying your pod got greedy and tried to use more memory than it was allowed. Both that and sudden slowdowns are classic symptoms that your applications are fighting each other for the same limited pool of resources on a node.
You see, Kubernetes is in this constant balancing act, right? On one hand, you want to pack as many workloads onto your nodes as possible to maximize utilization and save money. But on the other hand, you need to keep everything stable and isolated so one misbehaving app doesn't bring down the whole system.
And to really get how Kubernetes manages this balancing act, you got to understand the fundamental physics of the resources themselves. CPU is what we call a compressible resource. If things get tight, the system can just slow processes down. It gets throttled. But memory is incompressible. When it's full, it's full. There's no slowing it down. Something has to give. Something has to be terminated.
And it's this crucial difference between CPU and memory that leads us to the two most important tools Kubernetes gives us to manage our resources: requests and limits.
First up, we have the request. Think of this as a reservation. It's you making a deal with the Kubernetes scheduler. You're saying, hey, to run properly, my pod is guaranteed to need at least this much CPU and memory. Find me a node that can promise me that spot.
And then you have the limit. This is a totally different beast. This isn't a friendly reservation, it's a hard and fast rule, a ceiling. You're telling the node itself, look, no matter what happens, do not let this container ever use more than this amount of resource, period. It's your safety net to prevent one container from hogging everything.
So what's really fascinating here is how this table shows a clear separation of powers. The scheduler uses requests before your pod even starts to decide where it should run. But the limits, those are enforced by the kubelet on the node during runtime to make sure your running container plays by the rules. Two different tools for two different jobs.
Okay, before we go any further, let's talk about a super common and honestly pretty costly mistake a lot of people make. It all comes down to the units you use for memory. So let me ask you, is 1 G of memory the same as 1 JIR?
The short answer? Nope, not even close. Using the binary unit G for gigabyte actually gets you about 7.4% more memory than a decimal G for gigabyte. The punchline is, the operating system thinks in binary units. So always use me and G to avoid confusion and make sure you're getting the memory you actually think you're asking for.
Okay, so now that we've set our requests and limits, Kubernetes can start making some really smart decisions. When a node starts running out of resources, it knows that not all pods are created equal.
And the way it does this is with 3 quality of service classes, or QoS for short. You can think of it like a priority ladder that determines which pods get kicked off the node first when things get tough. And this is so important to get. By setting your requests and limits, you are literally programming how your pod will survive. Guaranteed pods are your fortresses. They're the last to go. Burstable pods are the flexible standard. And BestEffort pods, well, they're the scavengers, running on leftover scraps, and they are absolutely the first to be killed.
All right, we know how Kubernetes prioritizes pods. But what actually happens when a container tries to push past its limits? The consequences are very different for CPU and memory.
And this just perfectly circles back to the physics we talked about, right? If you blow past your CPU limit, you get throttled. Your application just slows down. But if you exceed your memory limit, there's no slowdown. It's termination. Your application gets OOMKilled. Now, with CPU, you got to watch out for something called the multi-core trap. It's a real gotcha. A CPU limit isn't per core, it's a total time allowance. So a multi-threaded app can burn through its entire time slice across all cores super fast. leading to these sudden, brutal pauses and huge latency spikes you just can't explain.
And when it comes to memory, when that killer comes knocking, you're going to see this number, 137. If you see that exit code, it's a clear signal. It means your container tried to allocate more memory than its limit allowed, and the system had to shut it down.
Okay, so we've got the mechanics down. We know the rules of the game. Now, how do we use all this to stop fighting fires and actually build stable, efficient systems from the get-go?
Well, at the cluster level, you can enforce good behavior. Resource quotas let you set a hard budget for an entire namespace, saying this team can't use more than X resources in total. And limit ranges are awesome because they can automatically apply default requests and limits to any pods that don't have them set.
And for your own apps, here are the golden rules to live by. First, always set requests. Never run as BestEffort unless you're okay with that pod being killed first. Second, for memory, always set your limit higher than your request to give your app some headroom. And third, for your most critical workloads, your databases, your message queues, make them guaranteed. Protect them.
And this brings us to a really interesting debate in the community, the CPU limit controversy. For some apps, especially the ones that are super sensitive to latency, you might actually want to remove the CPU limit altogether. The argument is that the risk of that sudden, unpredictable throttling is actually worse than the risk of the container using a bit more CPU. So what's the big takeaway here? It all boils down to this core idea. You use requests to guarantee your app gets the resources it needs to be scheduled, and you use limits to protect the system from your app running wild and abusing those resources. If you can master that duality, you're well on your way to a rock-solid platform.
And I'll leave you with this final thought to chew on. Take a hard look at your current setup. Is it possible that your resource settings, the very tools you're using to create stability, are actually, unintentionally, causing the very performance issues and instability you're trying to solve?